Now, you may be wondering what number bases are because you might not have heard of it or been taught about them before or learned about them before. So, number bases are when the same number can be represented in many different ways, and the methods that are used to represent these numbers are known as bases. The numbers based on how many characters are available for representation of numbers in that base. So, this might be a bit confusing, so let's break it down. Um, Certain numbers can be, or every number can be represented in different forms. And the one that we use is base 10. And it's sometimes called denary or decimal, but it is base 10. And its characters span from 0 to 9. So we say that the number that the base is, so base 10, the reason that it's base 10, is based on how many characters are available for representation of numbers in that base. And that means that the amount of characters we have available are 10. We've got 0 to 9. If you think about it, the number 36 is represented with 3 and 6. That's only two numbers. 36 isn't its own number, it's made up of two others, if you see what I'm trying to get at. And so there's only 10 characters available for representing numbers in said base. So base 10 is what we use, called decimal or denary, and its characters span from 0 to 9, meaning that there are 10 in total to be used to represent any number that you want. And all numbers are denoted with a subscript of the number of the base that they are written in. In all of our examples, we will be using the number 16 so that you kind of understand. So just keep in mind that every number you're seeing as an example, or most numbers that you're seeing, will be 16. So let's talk about base 10 a bit more in depth first. Hopefully you've understood what I've said here. Now, decimal, denary, or base 10 is what humans use to count. We use 10 digits to represent any number, and this might actually be because humans have 10 fingers. Little fun fact for you there. Now, as you can see, decimal and denary numbers are denoted with a subscript 10. So this number is 16, and this is the base here, just so that we understand that it's been written in base 10. 16 is the number, base 10 is our base. Base 2 is binary, and this base only uses 2 digits, hence its base 2. Those 2 digits are 0 and 1. And this base is what computers represent with. Computers easily represent these two values using a high or low current. And you should know how to convert into and out of binary. So once again, you're seeing 16 here. If you don't know how to convert into and out of binary, or if you do and you just want to check that I'm right, or you need me to prove it to you, you can see that this is our number, and it's base 2. So now I know, oh, right, well, it's not 10,000 because it's not base 10, you see? So I know that that's our number, and that is our base. So since it's base 2, we know it's binary, and we know binary goes up in powers of 2. So 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and it keeps going up, which means that it's 1, 2, 4, 8, 16, 32, 64, 128. Now you can see that these are all zeros, which means that we're not representing with that. This is a 1, so we keep it. That, or that. We add up all our 1 values. Well, this is 16 plus no other 1, so nothing else, which means that the value we've represented is 16, but in base 10. So yeah, hopefully that makes sense to you. Base 16 is hexadecimal, and adding on to decimal denary in a way, hexadecimal uses 0 to 9, but also A to F to represent the numbers 0 to 15. You should also know how to convert into and out of hexadecimal. Once again, this is the number 16, and interestingly enough, I don't know why, but 10 base 16 is equal to 16 base 10. I think that's just kind of funny. A little silly thing right here. I think that's kind of cool. But this does represent 16. And if we bring it over here, 1 and 0, right? This is in 4-bit binary. So how do we get 1 in 4-bit binary? Well, we do 0, 0, 0, 1. And this is 0 in 4-bit binary. How do we get that? Well, it's 0, 0, 0, 0. If we join these together to create 8-bit binary, we have 0, 0, 0, 1, 0, 0, 0, 0. And before I even convert this, let's just look at the last slide. 3 zeros are 1, 4 zeros. 3 zeros are 1, 4 zeros. So we now have proof that this is all the same number. Hopefully this is making sense so far and you're following along. If not, I'm sure there'll be help in the description or in the comments, or if you need to watch this video a few times to kind of understand it, that's okay too. There should be a video up soon on questions, on hexadecimal different bases, how to convert between bases, and more. You can also check my shorts where I might try to explain it again, and hopefully you kind of understand that too. Now, I've actually expanded on hexadecimal on this slide or page, and it's a very clever concept. It's able to efficiently make up any number using just 16 digits. And of all of the number bases, hexadecimal is the most compact. For example, a number like 733,452 uses 6 digits in decimal or denary, which is our base 10. It uses 20 in binary, and they're listed here as you can see them, but it only uses 5 in hexadecimal, and those are B310C. Converting between hexadecimal and binary is easy, and you can see I've put as you'll soon discover, so there are slides coming that will demonstrate again, and hopefully slowly and hopefully slower and easier, but I did just give you a little preview there, a little demo. And its compact nature and ease of converting makes hexadecimal an amazing shorthand representation for binary. So let's do some conversions. Let's convert from binary to decimal. Now you can convert between binary and decimal by placing value headers above each bit, starting with 1, which is 2 to the power of 0, and increasing in powers of 2. You should know that any number to the power of 0 will always equal 1. And if you want an explanation of that, I should have a short up on it, but just know that any number to the power of 0 is 1. All of the place values with a binary 1 below them should be added together, and your final result will be a decimal or denary equivalent to the binary number you entered with. Now, converting from denary to binary is pretty much the same, but obviously in reverse. Use the same place value headers as before, starting from the right side, placing a 1, which is 2 to the power of 0, and increasing by powers of 2, placing the larger numbers on the left. And then starting on the left, if your number is less than or equal to the placeholder number, you should place a 1. Place a 0 if it isn't. Once a 1 has been placed, subtract the value of that placeholder position from your number and move on to the next one on the right. You should then repeat these steps until you have completed your conversion. Once every placeholder value has had a 0 or 1 placed underneath it, we should have our answer. Any leading zeros, so any leftmost zeros up until the first 1, are removable, even though you might be better off making it a whole number of bytes, so any multiple of 8 bits. Remembering that 8 bits makes a byte, and the amount of characters in your binary string is how long in bits your string is. Now let's convert from binary to hexadecimal. The first step of this conversion is to convert the binary number into nibbles, remembering that a nibble is half a byte, so a nibble is worth 4 bits. Each binary nibble is then converted to denary, as if it were 4-bit binary. Afterwards, you should convert to each nibble's binary equivalent, and finally the values should be concatenated or joined together, which is what that word means, to form the final hexadecimal value. Now, converting from hexadecimal to denary, it's usually easiest to convert from hexadecimal to denary via binary. So first, convert your hexadecimal value to binary by converting each hexadecimal digit to a denary digit and then to a binary nibble. So we'll do that slowly on the screen with little labels so that you can see what you're doing. Then combine your two binary nibbles and convert from binary to denary for your final denary value. And then the other way around, converting from denary to hexadecimal, is basically the reverse of what you've done again. Convert your denary number to binary, split it into nibbles, convert each nibble to denary by themselves or independently, and then convert the denary to hexadecimal. Once you've joined together your final hexadecimal values, you're done. These are my sources for this video. I hope this was decently easy to understand. I know it's a tough topic, but I hope I explained it well. I hope you learned something. If you did, consider liking and subscribing to support and get more content like this. Thanks for watching, and goodbye.